Okay, wow. We're the duo again.
One more time.
Yes, one more time. This activity came from our search, I guess, for answers as we went to various meetings across the country, national science teachers conventions, and we asked people about what they thought about NASA materials and what worked with them in the classroom. And it was like a questionnaire. And one of the things that was mentioned by middle and high school teachers was that teachers wanted to have real NASA data used with activities in the classroom. And we talked about textbooks before, and I heard a moaning and groan out there. And so often those materials are kind of manufactured and not necessarily something that's real. And we put together an activity where you're going to be looking at the solar system like you've never looked at it before. Now, when Bonnie gave her presentation, we had some interesting pictures of Saturn, and we recognized some things there. We're not going to have some pretty pictures, at least not yet. But what we're going to do is to look at real data. And we're going to analyze that data and try to figure out some things about our solar system. And Frank, would you agree that they're going to come up with some new ideas about the planets in our solar system and how things work?
Well, I would say that they're going to uncover for themselves the solar system, and I, as an authority, am not going to tell them
Excellent.
the answers.
So this is going to be a real inquiry-based kind of activity.
Oh, you might mention scientific inquiry. Well, first of all, the name of this, we call it a mixed-up solar system, okay? We are purposely going to hide things from you. All right, so if we ask you not to turn to the pages beyond, look at the page that we're on, we are hiding things from you on purpose. It is for educational purposes. All right, so first thing we're going to do is we're going to talk about scientific inquiry, okay? Now, I'm not an educator. I'm an astronomer. I have been trained in the inquiry-based method of teaching. But everything I've learned about it is that it's the exact same thing as what we do as an astronomer. As an astronomer, if I'm going to publish a research paper, the first thing I'm going to do is I'm going to figure out what questions I have to ask about whatever topic it is I'm going to study. Okay, I have to come up with a question that I want to answer. In order to answer that question, I've got to come up with some evidence. Okay, and I've divided the evidence into two parts, because generally you go out and you collect your data, and then you've got to analyze your data. So actually, that's in astronomy, that's a huge step, because going to the telescope and just collecting the data can be a very laborious process. And then once you've got the data, you aren't anywhere near done. You're just beginning, because you then got to take that back to your class, you take it back to your lab, and you've got to analyze that data. Once you come up with some analysis of that data that tells you something, you then have to figure out, what does it mean? You come up with some explanation. All right, well, based on this data, I say this. All right? And you want to make connections, because other people have used similar data to come up with other explanations. And if you can't relate to their explanations, if your explanation is so totally off in left field, nobody's going to believe you. Okay? You've got to make connections between this data and other explanations. And finally, publish or perish. If you do not communicate your ideas to other scientists, you are totally useless. A scientist who sits alone in his laboratory and uncovers incredible secrets of the universe is absolutely useless to society as a whole if he does not communicate that to others. Science is a collaborative process. All right, so all of this is exactly what we're going to ask you to do in our exercise today, and it's exactly what you should be asking of your students if you want to teach them how to think like a scientist. And this thinking is not just related to science. It can be related to any other subject matter that you're studying, being able to critically think through this process. Okay? So, we're going to start with a precursor, a pre-engagement activity about scientific notation and scientific plotting. Because numbers in astronomy are, to be obvious, astronomical. All right? We can't cover those numbers and do linear plots. All right? They cover a much wider range than we can do with linear plots. So we have to use scientific notation, which you generally don't get until later in your years, but we have done this exercise with a wide range of kids, and they could all get it if you present this as a pre-activity first. So, in your packet, you have the scientific notation and scientific plotting packet, which you can take out now. And it has various stuff. It has this introduction, which is lots of words that you can read at your leisure later. I'm not going to bother, skip through this. Boom, let's go to the next thing. Turn to the next page, and we've got a table of data on animals and insects, okay? First column is the various types of animals. Second column is the family size, or the colony size. All right, and the third column is the average length of an individual. Now, if you look at that second column, you can see that the range of numbers goes from 1 to 400,000. All right? And you can imagine that that is such a wide range that if you tried to plot that on a linear plot, okay, how would it look? You in the blue shirt over there. I'm going to pick on people at random, so you have to pay attention, okay? I am not a fair teacher. I come in, I call you at random. And especially if you look like you're not paying attention, that's what I'm going to call on you. All right, you in the blue. Can you imagine what it might look like if we plotted that on a linear plot? It's not in the book. The answer, there's no answer in the back of the book. You have to think. Sorry.
It'd be a huge range.
It'd be a huge range, okay? All right, anybody want to go further on that?
Which column are we
We're talking this one, this column here. Okay.
It's very inaccurate, because you wouldn't be able to put it on a piece of paper and say 400,000 is down here in one.
Right, okay?
Yeah, it would just be really misleading.
Be really misleading.
It would be grouped. It
Okay.
would all look like they're the same number.
Right, all of the small numbers would look like they're effectively 0. And the only two you'd be able to see is 100,000 or 400,000. People get that? Okay, so you'd have 2 points and then you'd have all these points down here. You wouldn't be able to differentiate between them, okay? Now that's how we would normally plot things on a linear plot. However, if you plot it like on the next page, you use what we call mathematical logarithmic plotting, or we have called it in here to make it friendlier, scientific plotting. We find if you say logarithms, people go, ooh, ah! Math phobias jump up like crazy. How many people here admit to being math phobic? How many math teachers admit? I know, we have a lot of math teachers, so we shouldn't have too many math phobic people here. But a lot of your students will be math phobic, right?
Yes.
They see numbers and they go, ah! All right. If you, however, take your axes, instead of putting 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5, etc., if you put their actual numbers there, and then you explain that instead of a linear progression, an additive progression, it's a geometric or multiplicative progression. So that the difference between 1 and 2 is the same as the difference between 2 and 4, same between 4 and 8, and so on up there. So that distance on the y-axis is a multiple, all right? The same distance on the y-axis is the same multiple. It starts to help. But the most important thing is to put the numbers in a friendly manner, all right? We find that putting numbers in a friendly manner, most kids down through middle school can get this and not worry too much about it, okay? We've even done it with some 5th graders, and they were okay with it.
8th grade.
8th grade, we did some younger ones too.
too.
Yeah. All right, so you can see that we have plotted on here the 400,000 and the 100,000, but yet you can still differentiate between the 150 and the 9 and the 7 and the 1. And actually, when we did this on Tuesday, somebody went, oh, the poor panda, family of 1, all alone. That was one of the first times I got that. It's kind of funny. All right, so what you can then do by introducing this to your students, you can then go to the second plot and the average length of an animal. And we give this to you unfilled out so that your students can go through it and fill it out for themselves. We're not going to ask you to do that right now, but this would be a good pre-engagement activity to get them used to scientific plotting before they do the activity. All right, and here is the filled out plot. You'll notice in the upper right-hand corner there's a T on this. That stands for teacher pages, okay? So you have the answers. These are the answers in the back of the book, but it's just a plot. All right, any questions on this pre-engagement activity? Math teachers, what age level do you actually teach logarithmic plotting like this? Anybody know? What age level do you introduce scientific notation? 7? Yeah, 7th and 8th?
It's not in 6th grade.
It's not in 6th grade. Okay?
I teach in 6th grade.
She teaches it in 6th grade, but she's got the gift.
We have a brand new math program, the Singapore math program, which is right off the coast.
Okay, cool. All right. Any other questions on this? All right, moving forward to the real activity. Now we're going to go to this mixed up solar system. This is an inquiry-based activity using real data, graphing, and analysis to teach the methods of science. Okay, you may come out of this with a really cool understanding of the solar system, but that's not really what we're teaching you. Okay, even I, as the astronomer, know that the most important thing we're teaching you is the methods of science and how to understand the world around you. And as you know, in 2006, a certain favorite, small, pathetic object out at the end of the solar system was demoted, officially, although it had been demoted by others earlier. And we got a lot of debate about it, especially in the popular media. So this becomes a vehicle for which you can use, you can start a discussion within your classroom about scientific debate. And of course, just to be fun, I call it a super search through 16 solar system subjects for scientific significance. So, your mixed up solar system packet is going to contain all these wonderful things, but we're not going to give you all of them at once because we know you will look forward to see the end. And so, Dan, what do we pass out first?
Okay, first we have the data.
All right, so the first thing we're going to pass out to you is the data. And if you look up on these slides, we are going to maintain our objectivity, okay? We are not going to tell you what these objects are, all right? If I tell you one of them is this and one of them is that, you will have preconceived notions. So we just have objects with numbers. So this is your data table. Objects 1 through 16. We got them passed out. Everybody got a data table? Okay. Now, when we do this with the humanities teachers, a lot of them look at the data table and they have their math phobia jumps up at them. Okay? Yes, there are people. On the other hand, when we do it with some science teachers, especially that one teacher in Baton Rouge, they look at this and go, "Ooh, cool! This is great! I love it! There's so much we can do with this." Right? So I don't know which side of the spectrum you're on. Okay, it's okay if you're on every side of the spectrum, all right? We're going to go through this data table and just understand it. Okay, so the first column is object number. These are randomized. They we're not telling you what they are. Okay, so there's no particular order to them. Column A is number of moons. Okay, so you can see there are a variety of numbers of moons around these objects. Column B is orbit shape, where 0 is a circle, and 1 would be a straight line, but none of them go up as high as 1. I think the highest one is what? Around 0.44 or something like that. So it's basically from circular to more elliptical. Column C, we have the orbit tilt, where there is a flat orbit, which others are compared in terms of tilting in a matter of degrees. Column D is the distance from the sun, which is the radius of the orbit in millions of kilometers. Millions of kilometers is the unit here. This is also the average radius, because these things do have elliptical orbits, and elliptical orbits are one foci is closer at one time, so we do the average of that. Column E, we start getting into scientific notation is absolutely necessary here. This is mass in 10 to the 26 grams. And you may say, why do you use grams? Well, if we use kilograms, it would still be 10 to 23rd kilograms, so it's not really, we still have to use the scientific notation. It's just habit in astronomy that we came up with using grams. Okay? Why? I don't know. That's just the way it is. Okay? The size in column F is the radius in kilometers. And the column G is not mathematical, it is verbal, it is composition, and there are 4 different compositions: rock, gaseous, rock and some ice, ice and some rock. You'll notice one thing that we've done. If you look in column E, you'll see that there's a gray line through all of the decimal points. to line them up. Some people say, "Oh, that looks ugly because you haven't centered everything in your Excel table." And no, that's on purpose so that we line up all the decimal points so that you can see things. All right, so right here, tell me something about column E. Can you find the largest thing in column E? Yes, what object is largest? Has largest mass? 7. He says 7 has the largest mass. We agree? Okay. Over here in the black shirt, sir. Tell me what has the smallest distance from the sun? 13. People say 13. We agree? Okay, great. Now, I do that to show you that it takes a little while to search through a table of numbers. All right? Tables of numbers, one, evoke math phobia amongst a lot of your kids. And two, finding information in a table of numbers is not always that easy because you have to search through and compare, especially when they're jumbled like this. What would be a better way to explore data? Spreadsheet, okay, or especially for the high school kids. We're not going to do spreadsheet today, so what might be a better way? Graphing, thank you very much. Okay, so we want to be able to graph this, all right? So, next thing, we're going to look at each of the single characteristics in its own graph. So now we pass out the next thing. Okay, and please stay on the graph that we're on. Don't jump ahead. Okay, so if you look at plot A, which is on the top, we've got the number of moons. Okay, and now that we've plotted it like this, let us ask this lady over here in the black sweater. Okay, tell it. No, this is going to be so easy. I'm making it really easy for you. Tell me one thing. You don't have to come up with all the answers. Just one thing about this plot. Just anything.
The objects are numbered in the same order.
Okay, the objects are organized in order along the x-axis. Okay, great. I've had kids say the dots are red. Okay, great. That's something about it. Okay, all right. All right, you're laughing, so you get to say the next one.
Objects 1, 5, 6, 11, 13, and 16 have 0.
All right, it looks like certain numbers have 0. Okay, now, question. Can you tell for sure whether that's 0 or 1? Okay, this is the problem with graphing, right? Because this was graphed by a graphic artist at our Kathy Cordes at Space Telescope, and she didn't use Excel. She just plotted them by eye. All right? Can she make mistakes?
Yes. Sure.
Yes, everybody can make mistakes. So by eye it looks like 0, but you can't tell exactly. And if you wanted to tell exactly, how would you do that? Say that louder. Go back to the data table. Right. So the data table is better for getting the exact numbers, while the graph might be easier for other things. Okay? So, I haven't called on you yet. Tell me something else about this.
7 has the most moons.
Now, object number 7 has the most moons, and I got to tell you that's probably the number one response I get to that question, right? Tell me something about this. It's easy to see what has the most, the largest. Largest and smallest are often what you will get. Okay? How about you? Can you tell me something else?
Most all have less than 5.
Okay, there are a lot of them that have less than 5 moons. How many of them? All except 4. Okay, so 16 minus 4 would be 12. 12 objects have less than 5 moons. Okay? Anything else somebody would like to tell me about this graph? You can raise your hand, you can call out.
Who needs to sign the table? I'm sorry to interrupt here, but I keep being said, pass this way. Who needs to sign this?
Who hasn't signed whatever they're supposed to sign?
Sign sheet.
The sign-in sheet.
I know what it is. I'm asking who still has to do it.
Send it over.
Yeah.
We have our scoff.
I understand what purpose of this was.
All right, now that we've taken care of the sign-in sheet, Anything else about this? Anything else about this plot that somebody'd like to say?
The mode is 0.
What?
The mode is 0.
The mode is 0. We're talking mean, mode, and average, and all other things, which you could do better from the. There is no pattern. Great, I like that. Okay, so let's make an observation. All right? Let's make a generalization. We've looked at one plot. Based on plot A, finish the sentence. Objects in the solar system, right here. Finish that sentence.
I have no idea, we're talking about moons.
Okay?
Moons in the solar system.
Okay, but based upon this, is there a generalization you could make? Most objects in the solar system, she finishes it as have less than 5 moons. Okay? All right? When I put together this PowerPoint, I said generally have few moons. Okay? So from one plot, we have gotten a piece of information about the solar system. Okay? Or at least of these objects in the solar system. I want to emphasize that everything we're going to talk about today is based upon the selection of data. You've only got 16 objects. Okay? This isn't everything in the solar system. But based on these 16 objects, you can say that most objects in the solar system have few moons. Is that a reasonable conclusion? You can write that up on the board, have your kids write it down. They would have, after looking at one plot, a nice idea, okay? That's cool, isn't it? All right, let's move on to plot B, orbit shape, please. All right, you'll notice our artist has done for the y-axis a nice explanation. Instead of putting just 0 to 0.5, which is kind of cryptic, except for those of us who understand the concept of eccentricity. It's a measure of the ellipticity of the orbit. She's drawn in circular to semi-elliptical, okay? All right, let's see who to pick on this time. Over here, you're wearing purple, so you caught my eye. Tell me one thing about this plot.
The majority seem to have a shape that is more circular, a shape more towards the circular.
Okay, you're going for the generalization right off the start. She says the majority seems to have a shape that is more circular. Okay? In the striped shirt over here, can you give me something else?
Well, let's see. I mean, you've got this randomized, so there's always never gonna be a pattern here.
All right, he says the randomization is working. There is no pattern. Okay, how about right here?
I'd say there's one oddball in terms of ellipticity, and then all the others are sort of grouped.
Okay, he says there's one oddball. What is the number of that oddball?
Number 4.
Number 4 is an oddball. Does everyone agree?
It's an outlier.
Anybody disagree?
I was just gonna say it's an outlier.
Oh, instead of saying oddball, she's using the mathematical term outlier. Why would you say it's an outlier?
Because in terms of all the other data, it's way outside the data range.
Okay, it's way outside the data range. All right, so the idea of an outlier, when you're talking graphing, is if you were looking, if you were doing a histogram of them in terms of orbit shape, you would have a relatively consistent histogram, and then there'd be this empty region, and then there'd be one out here. Okay? All right, and it's partially due to the way we plotted this, that there are these lines here, and there's nothing in this section. There's one in this first region, there's none in this second region, there are several in this third, several in the fourth, and a lot in the fifth, right? And that sort of guides your eye into looking at it as an outlier, but I would agree it's an outlier. Anybody want to argue it isn't an outlier? And please, feel free to disagree. This is science, for heaven's sake. You know, we are here to disagree. You know, that's what I was trained to do in graduate school.
I mean, none of them have a greater than 0.5.
None have greater than 0.5, so what does that tell you?
Relatively circular.
They're all relatively circular, okay? Ellipticity can go all the way up to 1, all right? And none of the 16 objects we've chosen here go beyond 0.5. Yeah?
I'd be inclined to say it's not an outlier,
Okay, good, I love it.
because there's no relationship between the objects, they're independent events.
Right?
Doesn't an outlier require that its information not be consistent with the pack because the pack's related?
Well, I guess the relationship in this pack would be that the pack are all objects in the solar system. Now, if there are different groups within that pack, you know, that's all you know at this point, is that these are all objects in the solar system. Okay? All right, yeah?
So is that one 2 standard deviations outside the mean?
Okay, so now he's getting to the mathematical definition of what an outlier would be. And it's a number of standard deviations outside of the mean. Okay, I don't know. I've never calculated the mean and standard deviation. Okay? But that's something you can do with your students, right? All right, Bonnie, write that down. Calculate the mean and standard deviation of all of these characteristics. All right, we can do that. That's something to add to your going beyond. All right, anything else about this plot that somebody would like to say? Yes?
Most, 9 out of 16 are between 0.0 and 0.1.
Okay, 9 out of 16 are between 0.0 and 0.1. So that's just over half, so you could say most are between 0.0 and 0.1. Good, good. Anything else? Okay, let's make a conclusion. Based on plot B, objects in the solar system, I'm going to ask this lady right here, typically have a more circular orbit than elliptical orbit. Okay, and as I put it in my thing, generally have mostly circular orbits. Okay? 2 plots, 2 conclusions about the solar system. Kind of cool, right? Plot C, please. Orbit tilt. Okay? And you there in the pink, you caught my eye. So can you tell me something about orbit tilt? Just one thing. Now you'll notice I asked for just one thing and I let it be anything because some people are afraid to speak up. And so my technique for trying to get them to speak up is to try and say, just give me anything as small a nugget as you can. Okay, object 4 has the most tilt. Once again, trying to find the max and the min is usually an easy thing to do. And if your students don't want to respond, you can just ask them, well, which one's the largest, which one's the smallest, to prompt an answer. Okay? Who hasn't said anything? Over here in the coat.
I would say that the majority of them have a smaller tilt.
Okay, the majority have a smaller tilt. Okay? We want to quantify that number as what small means?
10.
Around 10 degrees or less, right? Okay, that's good. All right? Over here in the blue shirt. Do you have anything else to add?
I was going to say 10 have a tilt less than 10 degrees.
10, or number 3 looks like. Here, any outliers?
No,
Why not?
because, number 4 is at 42 and the closest one to that would be at 35. It's too close to be an outlier.
Okay, you have a relatively more continuous distribution. If you take 9 in the first bin, there are 2 in the next bin, 2 in the next bin, 1 in the next bin, 1 in the next bin, right? And that seems a relatively connected distribution. Doesn't seem like there's a gap in between any of them. All right? So don't feel like there are any outliers here. Anything else anybody wants to comment about this plot? All right, let's move on and say plot observation based on plot C. Objects in the solar system. You there in the polka dot. You've already said something. I'm sorry. But gentleman next to you. How would you finish the sentence? Based on plot C, objects in the solar system.
Have a relatively horizontal tilt.
All right, have relatively low tilt or a very, very small tilt. What did I say? Generally have low inclination orbits. Okay, that's just the way I put it. Let me just stay straight out. I hated putting these slides in, but it's nice to be able to have them up there because I don't want to say that these are the answers, okay? These are just the way I put it, all right? My number 1 point for you today is if you can back it up by the data, then it's a scientific observation, okay? If you can't back it up by the data, then it's just, noise, all right? Whatever you try and make as an observation, as a conclusion, must be backed up by the data. So however you specify it, however you say it, is fine with me. All right, Move on to plot D, distance from the sun. All right, who should we pick on for this one? This gentleman over here in the green shirt. Tell me something about plot D.
The projects we're looking at are between 60 million and 10 billion.
All right, 60 million to 10 billion kilometers, yes. 60 million to 10 billion kilometers away from the sun. Okay? All right, that's good. All right, over here, the gentleman in the orange shirt.
Yes, sir.
Yes, can you tell me something about this, something else about this plot?
It looks purely random to me. I have a hard time finding anything there.
Okay, it says it looks random, okay? What do we call a plot that looks random? Math teachers? Scatter plot, okay? All right, how many people think this is a scatter plot? How many people don't think it's a scatter plot? How many people are too wimpy to vote? All right, those who might say it's not a scatter plot, speak up.
Scatter plot is any plotting of data, and you're trying to look for the correlation via the scatter plot. So
Okay.
plot of data is a scatter plot.
Okay, so taking the type of plot to be a scatter plot in terms of this. Usually, when we have a randomized distribution, I as an astronomer call it a scatter plot, if I don't see any correlations or anything. So maybe I'm using that incorrectly. Go ahead.
Zero correlation.
Zero correlation. All right, are you going to use zero correlation?
Every single one is
It's a scatter plot.
If you want to use scatter for a type of plot. Okay.
Because object number is piece of data. Now,
Finding a correlation between the object number its deception.
all right. Just basically a statement of fact.
Okay, so we have a definition discussion going on here.
That's true, because the scatter plot has to have correlate two
All right.
pieces of data. You're not correlating two pieces of data.
Try to tell them about what kids say, in transforming the working with children, or how they respond.
All right, the kids would basically, when we work with kids, they would get very frustrated at this plot, okay? Because when they were looking at the other plots, they could see that, oh, all the things are here, or most of the things are here, and only a few things are there, or vice versa, okay? And they would get very frustrated at this plot because they couldn't see a pattern to it, right? When you don't find a pattern, that's actually a good thing, all right? And so, yes.
Are they also more frustrated because compared to plot A, this is the first logarithmic scale plot?
Yeah, usually I start this plot off with by saying, yes, this is the first logarithmic plot, but they didn't actually bother them, okay? The students we worked with, having done the initial preparatory, when you introduce this plot, I should have said, okay, now notice that this is a scientific plot, that we're using geometric progression on the y-axis. So my apologies for not doing that as soon as we introduced it. But when you do that, once you introduce it, they can see the numbers and they can figure out the numbers. All right. Anything else about this plot that people would like to say? Yes.
13 is closest to the sun, and
Object 13 is closest to the sun. You're seeing two things. Sorry. And number 4 is the farthest from the sun. Okay. Anything else? Over here. Yep.
You're starting to get two bands out there. There's two groups.
Yeah.
Okay. 2 groups.
Yeah.
Tell me your groups.
Well, look, between, about 350 million and 500 million, you got like 4 dots.
Okay.
And look at the inner solar system, you've only got a couple dots scattered out. At the very top, you're starting to see, once again, there's a lot of dots pretty close to each other. I mean, the distance gets bigger up there, but still, they're clumping together.
Okay. So if we plotted that in a very fine histogram along the y-axis, you think we might get some empty regions?
Yeah, there's 2 big dots in the middle.
Yeah, I don't know. We could try that to see. What do you got? What is it? What does everybody else think?
I agree with him, it's more of a band here and a band up there.
Okay. So you're seeing a band across here and a band across there. These 2 guys, if you ignore them,
That would be
I
the
can
top
agree.
one.
Then you've got these few guys along here. If you ignore them, then you get the 2 bands. All right. Anyone want to disagree? We like disagreement here. Yeah. So she's noting over here, you can almost look at a band between 100 and 1,000 and 1,000 to 10,000. But how much of that is guided by the fact that we plotted it with extra heavy lines at the 100 and 1,000? All right, you squint your eyes. Okay, a useful thing for trying to define patterns in plots: squint your eyes, so you can only see the dots.
There's a pattern.
I see a circle over on the left. See that? I see a nice hexagon right there. All right, somebody sees the Big Dipper. I'm not sure I see the Big Dipper, but you're allowed. Oh, okay, so we're talking Big Dipper here? Okay, there we go. That could be the 7 stars of the Big Dipper. Or are we talking across here?
There you go.
Okay. All right. By the way, constellations and seeing constellations in groupings of dots like this is a very, very powerful human ability, okay? We do this all over the place. Matter of fact, there's a plot up ahead where I'm going to make a joke about it, because every astronomer sees it. Yes?
There is a pattern because bigger, smaller, bigger, smaller, bigger, smaller.
Aha. Actually, if you connected them and go up, down, 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 up. Hey, that's cool! It's incredibly unintentional, okay? I chose the order of these 16 objects myself. That's totally unintentional. Nice find though. That's the first time somebody's seen that. Okay, so based on plot D, okay? Based on plot D, objects in the solar system, how can we make a generalization based on this?
They're not right beside the sun.
Say that louder.
No object is right beside the sun.
No object is right beside the sun, okay? Anybody else want to finish the sentence in a different way?
The one pattern that does appear to stick out is that there are no small distance objects.
Okay.
And I think that's a.
But in terms of the overall distances,
Overall, they tend to be all.
they are all over the place. People agree with that? And I agree that, yes, the observation that there's nothing really right next to the sun is important. Okay? That's an important one. You can get that from the plot. The way I put what you just said was have a wide range of distances from the sun. Okay? They're going from, as the first gentleman said, between around 60, 70 million out to 10 billion. All right, let's move to plot E, please, for mass. Okay? And I will do the first observation because every astronomer will go look in the lower left, and you see this? Yeah. That's the Great Square in Pegasus. We know that, okay? All right. The gentleman in the corner in the blue shirt, I haven't talked to you yet. At least I don't remember if we have. What would you say about this plot?
Even more scattered than the last one.
Okay, even more scattered or randomized than the last one. Okay, now I will give you a hint that if you tell your students they're allowed to say, oh, it's random, what are they going to say at every plot? It's random. It's random, because they're going to avoid having to actually think. He says it's random. Anybody want to agree or disagree?
Well, the majority of them are less than 10 to the 27.
The majority are less than 10 to the 27. Oh yeah, and by the way, this is a difficult plot because we have to use scientific notation on the y-axis, okay? There's just no getting around it, okay? And so here it looks like a linear plot, even though it's actually a logarithmic plot, okay? And that's a little difficult, so this is the one to be a little careful with. All right, so you said that the majority are below 10 to the 27th, then I count 1, 2, 3, 4, 5, is that 10? And then 6 above. Okay, all right. Yes, you were going to say something?
Well, something I always tell my kids is to always look at how each axis is labeled, and it's just deceiving because it starts at 10 to the 22nd, so it would look like, I don't know, 11 is light, but it's not.
Right. 11 being 10 to the
I mean,
23rd grams
it's the
is not the weight of a feather.
One, yeah,
Yeah.
but it's not starting with 0.
Right. Yes, recognizing that there is no 0 point on this. 10 to the 22 is the lowest one on that. Very good point. Other points about this plot? Yes?
The range is huge. I mean, it's a factor of 10 to the 7, right?
Okay, the range is huge, factor of 10 to the 7th. We're going like the smallest one is around 10 to the 23rd, and the largest one is a little over 10 to the 30th. All right, 7 orders of magnitude. What's that in real numbers? 10 million, thank you, okay? When we say 10 to the 7th, okay, a lot of people won't get that, okay? If you say 10 million, it's a much more friendly, okay? I'm a big advocate of making it as friendly as possible, all right? All right, so we got a factor of 10 million between the largest mass and the smallest mass in these objects. Okay, anything else somebody would like to contribute on this? Yeah?
You got 4 really big ones up there. I mean, like,
4 really big ones.
I mean.
Okay? All right, they're around 10 to the 29th and 10 to the 30th.
And then drop
Okay?
off fast.
Does anybody have, well, all right, and do they seem to be a disparate group? If I squint my eyes, do I see any outliers, any groupings in here? I can sort of convince myself I might see some groupings. Can you, yeah.
Kind of like compare like object 6 and object 12, similar.
That's nice. Object 6 and object 12 look like they have pretty much the same mass.
You can do it again with 1 and 29.
1 and 9, yep, okay. That's cool. All right, anything else on this? All right. See how visually you're able to sort of come up with ideas that I don't think you would have been able to come up from a data table, right? And that's the sort of idea of going through these plots. All right. Based on plot E, objects in the solar system. How would you finish that question?
Have a very wide range of mass.
Have a very wide range of masses. I said have a wide range of masses. Okay? So, and again, my answer is not the correct answer. It's just an answer. All right? Anybody else have anything else they would put to that? All right, let's move on to plot F, size. Okay? In the blue and white shirt over here in the corner. That would be you.
Oh, hello.
Hi, how are you?
I'm just peachy. How about yourself?
I'm doing fine, but my voice is going to get tired.
So the size?
Yes, what would you say about size?
Wow. Actually, 7 cats is random.
It's random! Does anyone disagree with that? Okay, first of all. Okay, do you think there's a reason why I put these last 3 plots as the last 3 plots?
They look exactly the same.
All right, because they have some of the randomness to it. Because you don't want to start with the random plot, because then you'll lose your kids in terms of getting information on the other. All right, something else. Anybody at this table here? No, you're not allowed to do that. You're looking at plot F only. You're not look elsewhere. Sorry, I have to stop you. We'll get to there. We'll get there next. Okay, that's where we're going next. What? All right, so he was saying that it looks like you can have a grouping of below 2,000 and above 2,000. Okay? If I look at that, I think I would say that they seem tighter below 2,000 than above, and looser above 2,000. Something like that.
Yeah.
Yeah?
It appears that the gaseous objects are larger.
There is no such thing as gaseous objects here. There is no gaseous here. Shh. I'm stifling you because there's no gaseous on this plot. Is there any gaseous on this plot? Then stop it, okay? We are talking about plot F and only plot F. All right, and there's a method behind my madness. Okay?
You don't want the statement, this mirrors the last plot.
But we don't want that, okay? What you just said, I didn't hear, okay? All right, so plot F, based on plot F, objects in the solar system
Come in a wide variety of sizes.
come in a wide variety of sizes. Yes, you can get small, medium, large, and extra large in this solar system, okay? All right, so invariably when we're doing teachers, somebody notices something in the plots, okay? And we're going to go to, let's take our observations together, okay? Now, so based upon 6 plots, just looking at 6 plots, we have made 6 different observations. Objects in the solar system generally have few moons, they have mostly circular orbits, they have low inclination orbits, they have a wide range of distances from the sun, have a wide range of masses, and have a wide range of sizes. kind of cool. These are conclusions that you can make by simply looking at plots. And I don't think most people would get that out of just looking at a data table. Okay? So plotting is a powerful way to try and understand things. But you can go even more. Instead of just looking at plotting of one characteristic, we can take the relationships between characteristics. Now, okay, can you hold this? This is science. Take plot E and F, which are the last two plots, and they were the last two plots on purpose. Hold them up to the light. Okay, align them and hold them up to the light. I have done this 100 times in my PhD career. While I was doing my PhD and I had to understand things and look at things, I would print things out and I would hold them up to the light. What do we see that some of you have already noticed already?
Very close relationship.
They're very close. They look similar, right? We see this? Okay. Now, thanks to the magic of PowerPoints, you can put those down, and we can do it much easier by looking up at the board. Okay. Here's plot E, plot F. E, F. E, and F. Okay. PowerPoint is really good for doing blink comparisons. Okay. It's not good for a lot of other things, but it's really good as a blink comparator. Okay? What do we notice? We see that correlation that the pattern in mass is the same as the pattern in size. So, if we were to plot mass versus size, what type of plot do you think we would get over here about in the sleeveless?
They would be very similar.
Okay, we plot one characteristic versus the other, mass versus size. Okay? Speak it out loud. You're allowed to be wrong. You just said, she said linear. Okay? She thinks it would be a line. Anybody else have another guess? Yeah?
Well, it would be the log of mass versus the log of size.
It would be log of mass versus log of physics. Notice that both of them are scientific plotting. All right, so if we plotted logarithmic of mass, logarithmic size, we would get this. Okay? Now, notice that I am not plotting red dots now. Instead, we are plotting numbers, so that we can set to each number as here is its mass and here is its size. All right, we got a really good relative line plot here. What do we call this? We've said it before already in this exercise.
Positive correlation.
A positive correlation. Okay? Things that have larger mass will have larger size. Now, why would that be so? Okay, in the red and white, the blue and red stripe. I said, why might there be a relationship between mass and size? Okay, so he says the bigger something is, the heavier it generally is. Okay, bigger things, way more. Okay, you wouldn't believe how hard it is sometimes to pull that out of students. Okay, it's sitting right in front of me. We think it's obvious. Bigger things, way more, right? Sometimes it's very difficult to pull it out. Some other times it's just easy. All right, so let me ask a question. All right, you over there. I have an object that weighs 10 to the 26 grams. What size would you expect it to be?
10 to the 26 grams?
Yes, not you, her. I'm sorry.
It would be like
About 2,000 kilometers in radius. Okay, everyone see how she did it? She went to 10 to 26. She went up, down, well, that's about here on the line. That's roughly around 2,000 kilometers in radius. Okay? So over here, the one next to the blue and white in the black tank top. Supposing I had something that is 15,000 kilometers in radius. What mass would you expect it to have? Okay, 15,000 kilometers in radius. Over here, somewhere around between 10 to the 28th and 10 to the 29th, right? Sound good. Because we have a relationship established here, we can measure one quantity and get a pretty good estimate of the other quantity. All right? And how accurate or precise do you think this estimate would be? Relatively good, because there's not much scatter along this line, right? So, observation, based on plot H, objects in the solar system. You want to finish it? Because you just looked up at me.
Yeah, I wrote down.
Okay, have a positive correlation between size and mass. All right, you could state it more, I state it two ways. One, to try and be friendly, which is objects in the solar system with smaller, larger mass also have smaller/larger size. Okay, that's trying to be friendly. Okay, but the more mathematical way to say it is based on plot H, objects in the solar system show a tight positive correlation between mass and size. Okay? Now, here's the kicker. What does this tell you about another quantity? What is the relationship between mass and size? What do we call that quantity? Speak up louder.
Density.
Density, okay? So looking at this plot, what does it say about densities in the solar system?
They're pretty much.
They have to be similar.
They have to be,
Well, they have to be similar. 'Cause
have to be
that's the issue
similar,
that I had.
okay? If you go back to it, you can see that there is some scatter here, right? It's not an absolute perfect line. There's some scatter, but the relationship between mass and size, density being mass over size cubed, shows you that you can make a third observation based on plot H. Objects in the solar system have a narrow range of densities, okay? In actuality, that density range is about a factor of 5 to 10, okay? Which shows you just how much you can hide on a log-log plot, all right? If you want to hide errors in your data, you plot it on a log-log plot, okay? There's a roughly factor of 10 difference between the least dense and the most dense objects that I plotted in here, okay? And if we were going to do this for the high school students and more mathematically, instead of composition, we actually would have used density in that last column, okay? But to make it, since density can be an annoying concept to some younger ones, we put those into words, okay? All right, plot I. Oh, wait a minute, I'm not supposed to go there yet. Okay, what I'm supposed to say is, all right, so we did one correlation, that was pretty straightforward. What other two characteristics might you think would be correlated? Anybody have, anybody, shout out one.
Distance, mass, and number of moons.
Mass and number of moons, cool, that might be correlated, yeah.
Orbit, shape, and tilt,
Orbit, shape, and tilt, why do you say that?
because it's on this.
Oh, you're looking at, she's looking at the feet. Why? Give me a reason why. I'm not going forward until somebody gives me a reason why.
They both deal with the orbit.
Yeah, orbit, shape, and tilt.
They both deal with the orbit.
They both deal with the orbit. Okay, do you remember which one was largest?
4.
Number 4. And which one was largest than the other?
4.
Oh, usually that gets noticed and gets pulled out, okay? All right, we noticed that number 4 was an outlier in one of them, but it was also the largest in the other, okay? So I actually plotted every single one of these against every single other one of these in order to find out the various correlations. And yes, there are some correlations in here. Mass and number of moons does have a bit of a correlation. But the second most powerful correlation is between orbit shape and orbit tilt. All right. So let's take a look at this plot. I think most everybody has said something. So I'm going to call on somebody who I've talked to before. This gentleman here in the red shirt. Or the maroon shirt.
Maroon.
Okay, tell me something about this plot.
Okay.
Just one thing, you don't have to come up with the...
Most
Yeah.
elliptical form.
I'm sorry, what?
Object 4 is the most elliptical form
Most elliptical orbit and
and the greatest orbit tilt.
the greatest orbit tilt. Okay, so it's way out there. Okay, in the circle dress. Tell me something else. There's something elliptical. Okay, sorry. I couldn't tell whether that was just the shape of the dress on or whether it was really elliptical in the pattern.
Most of them are just a circular with the small tilt.
Okay. all right, as we concluded for each of these plots separately, most of them are relatively circular and most of them have small tilt. And so you can see a clumping down in the lower left, okay? That becomes apparent here. All right, somebody at this table. How about you? Because I just looked up and saw it. Actually, I haven't talked to you. No, dude, sorry, Mike, big apologies. All right, thanks.
There's not as much of a correlation, a positive correlation between orbit.
Well, first of all, is there a positive correlation?
It's not as tight.
All right, yeah, but first of all, the question,
Yeah.
establish that there's a correlation first, okay? All right? Then you can qualify the correlation, okay? So, yes, he says, yes, there is a positive correlation. And then your second thing is that it's not as tight as the mass versus size, okay? All right, anybody, especially the math geeks, want to go even further than that? What's the mean and standard?
I'm a physics guy.
Oh, you're a physics guy, okay, which is still, plotting and statistics of plots is very important in physics. All right? Anything else somebody wants to throw in before I go on to asking questions? All right, for you, if I have an object that has a orbit shape value of 0.25, what orbit tilt would you expect it to have?
I would have to say 10 degrees the way this is going. 18.
Okay. She says 10 degrees. Somebody else said 18 degrees.
30 degrees.
30 degrees. Uh-oh, uh-oh. What are we talking about here? Are you guys going to agree or disagree over here? Hmm? Oh, I love it when they disagree. I absolutely love it when you disagree. Okay. Can you tell exactly what it should be? All right. Therefore, what you would have to say for this is that there are a range of tilts, right? What range of tilts would you expect? How about you right here? What range of tilts would you expect? Somewhere around 20 and 30, okay? 8 is down around like 18 degrees, 16 is up at 35, so somewhere in this range, right? Okay? All right, how about the alternative? If we said we had a orbit tilt of 30 degrees, all right? What would you say in terms of what its orbit shape value might be? 0.15 to 0.25 is what I heard. Okay, so there is a range of orbit shapes that you would say. So, based upon this looser correlation, you can make an estimate, but you're much more uncertain about that estimate. In science, we would say that has a larger error bar. It's tough to use error bars with the public because they don't understand the term error is actually a good thing, that you understand your error. We have to call it, for the public, we like to call it uncertainty. In mathematics, when you're doing this in physics, you have to say error bar because other people don't know what you're talking about. Okay? So for the public, we have a larger uncertainty in this correlation. All right? When we talk about it's a looser correlation. All right? So what do you think we're going to say here in our observations? Based on plot I, who would like to finish this one off? I haven't talked to this table here. So
I'll do it.
she'll do it. She volunteers.
Based on plot I, objects in the solar system have a wider range of positive correlation.
Okay? There's a positive correlation, but it's got a wide range between orbit shape and orbit tilt. Okay? How did I say it? Objects in the solar system that have a large orbit tilt tend to have a more elliptical orbit shape. That's indicating a positive correlation. This is the friendly way to put it. And notice I use the word tend to. Okay? All right? It's not an absolute. It's trying to be friendly using the word tend to. And then, of course, the more mathematical way to say it is objects in the solar system show a loose positive correlation between orbit tilt and orbit shape. Okay? Great. Where do we go from here? All right? The plot thickens. We're going to go size versus composition. And here's where you guys actually have to do something instead of just running your mouths. Okay? We are going to give you an empty plot of size versus composition. All right? And you are going to be the students who actually fill these things out, which is why you need your pencils and why we sat you at this desk, these desks. Okay, so go through your data table. Find each object. Figure out what composition it is, and in that composition's column, draw a dot with a number next to it. Okay? So for object number 1, what is the composition of object number 1? Rock. Great. What is the size of object number 1?
6,000.
6,000. So somewhere in this rock column, you go up to 6,000, you draw a dot and put the number 1 next to it. Okay? Lather, rinse, repeat for all 16 objects, please. There is no particular place you have to put it within the rock column, just somewhere in that rock column, okay? Rock and roll.
You know, like, with that,
I would just go one and prime by order.
Oh, okay.
So gas is weight number 2, and grid size is 25. So gas is number 2.
Okay, so that wasn't that hard, right? You're just plotting things, 16 dots on a logarithmic plot. All right, so the way our graphic artist did this, and again, this is not a scientist, this is a graphic artist, came up with a plot that looks like that. Okay? Does yours look something like this?
Yes.
Cool. And you plotted it the same way she did. I can't vouch that she did it perfectly correctly, because I have not gone through exactly and checked everything, but it's reasonable to my eye. All right, so what do we want to conclude from this? How about you in the blue? We want to give you one thing, okay? And again, only ask you for one thing. Give me one observation about this.
The gaseous, objects with gaseous composition have the largest size.
The objects with gaseous composition have the largest sizes. Cool? Everyone agree? Looks like it to me. Okay. Now, what else should we say? How about you in the pink here? Okay. The rock and some ice objects have the smallest sizes. Okay. How about a really basic thing that jumps out at you right from the first look at it?
There seem to be groups of
There seems to be
size and.
There seems to be groups in size and composition. Okay? So that if you have a certain composition, you have a certain size. I mean, did you expect that before you did this? Okay? Some of you said yes, some of you said no. I mean, how would we know? Right? Yeah.
Maybe I'm just not thinking about something that can explain why the smallest size are mostly rock and ice. And then as you get slightly bigger, you jump into getting more ice, less rock. But then once you get even bigger than that, you get rid of ice completely and go back to rock.
Yeah. Why would that be? All right. So he's wondering, you go from rock and some ice, then you go to ice and some rock, and then you go back to all rock. How did that happen? Yeah, okay, so he's wondering why, okay, which is really good, because that's the end result of science, is you're trying to explain why all these correlations you've got there, okay? You want to publish a paper in astrophysics, you're going to at least postulate why, as well as deciphering the correlation. Okay, one thing I like to do with the kids is talk about small, medium, large, and extra large. Okay, makes it friendly, again. So, what are the medium objects? We talked about the small. The small ones are, anybody? The medium, the large, and the extra large. Okay, and we see these groups. Okay? Now, is the separation between these groups clean? Pretty much yes. What What do I mean by clean?
We don't have any crossovers.
There's no crossover, okay? What's really cool about this, and when we first plotted this, to recognize you can draw a line and separate the small from the medium. You can draw a line and separate the medium from the large, and you can draw a line and separate the large from the extra large. Okay, so when we were looking at that size plot, which was all randomized, some of you were starting to see this, okay, and trying to see them in groups. Now, you couldn't see 4 groups in that plot because it wasn't plotted, it wasn't done in a way that you could see those 4 groups easily. But now that it's plotted like this, you start to see 4 different groups and sizes, don't you? Okay? All right, but it's emphasized because we separated them out by composition. All right, so observation. Based on plot J, objects in the solar system. You. I just have to look up and see you. Finish that sentence.
Objects in the solar system generally have the same size as other objects of the same composition.
Great. Objects in the solar system generally have the same size as other objects of the same composition. Okay, composition and size are correlated, right? How did I put that? I said with similar composition have similar sizes. Okay, cool. All right, did I have something else on this slide? I can't remember. All right, now the diabolical plot will be revealed when we do size versus distance. We're not going to ask you to plot size versus distance. We are going to plot them no, not yet. Not yet. We're going to plot that together. I saw. We're going to plot that together via PowerPoint. Okay. So again, log plot. Distance from the sun on the x-axis. Size on the y-axis. This size is the same as what we plotted in the previous one. Okay? So we're going to plot 1, 2, 3, 4. What do we see? Thank you. I set you up for that. I'm glad you were able to come up with a punchline. I thought I was going to have to go to Brandon for that one. Every astronomer will see the great square of Pegasus. All right. What do we see here? Is there any correlations here? Not from 4 points. Let's try 5, 6, 7, 8. What did we see?
They kind of look like they're clumping again.
Kind of look like they're clumping again. All right. 9, 10, 11, 12. Looks like what? Okay. Then let's do 13, 14, 15, and 16. What do we see here? Over here. How about, let's see, you. What do you say?
I see that they're showing the cluster and so we group them.
Okay, how many groups do you see?
4.
4. She sees 4 groups. All right? Somebody at this table over here. I haven't talked to you lately. Again, small, medium, large, extra large.
Yep.
All right, if I have small distance, then what do I have? All right, small distance from the sun would be large size, right? All right, so that's a correlation there. Okay, over at this table, I haven't talked to you lately. All right, if I had medium distance from the sun, what size would I have? Small size, okay? All right, let's see, this table, who haven't I talked to? You haven't said anything lately. If I have large distance from the sun, what size would I need?
Either extra large or small, or very small.
Extra large or very small? Well, I'm just sort of taking the group, so it would be this group up here. Yeah, the extra large sizes, right?
Yeah, I've got another idea.
You've got another idea, but you're trying to go beyond the scope, okay? All right. Okay, and finally back here, if I have extra large distance from the sun, I would have one of you two. Medium, okay? Everyone see that? Okay, so we're back into these 4 groups. That we got 4 beautiful groups here, okay? Now, so based on plot K, objects in the solar system, finish my sentence for me, you right here. That are similar distance from the sun have similar size. Oh, we should actually have plot K in front of you at this point, sorry. I shouldn't ask you to make a conclusion from a plot that you don't have in front of you. All right, but she said it right anyways. With similar distances from the sun have similar sizes. That's kind of funky. Sounds pretty much like what we just said on plot J, doesn't it? What did we say on plot J? Based on plot J, objects in the solar system with similar composition have similar sizes. All right? Isn't that what we said about plot J? Let's take a look at plot K and plot J together. Here we have plot K, here we have plot J. What do you notice? Same groupings. Now, should it surprise you that it's the same groupings in size? No. Not in the least, okay? Because size is being plotted on the y-axis. But, whoops, sorry, it's the groupings on the x-axis that might be surprising, okay? That it's not just distance and size, it's not just composition and size, it's all three of them together. So if I plotted plot K, I could circle these guys and say these are all gaseous. I could circle these guys and say they're all rocky. These guys are rock and some ice, and these are ice and some rock. What are we getting to here? Correlating composition with distance, with size. We're starting to do what we would call categorizing, classification, grouping of objects in the solar system. Okay? Now, here's the fun stuff. All right? You've been helpful, so I'll let you have some fun. Go to plot A. All right, take a look at plot A. Tell me something about plot A that we talked about, right? How many?
The majority that under.
All right, let's take a look at the ones that aren't under. Which ones are those?
Or that aren't, 2, 7, and 10.
And
That one, 14.
2, 7, 10, and 14.
And they're all.
So all of these objects have one other characteristic in common, and what's that?
Yeah.
They have a large number of moons. Kind of cool, all right? Now we're looking deeper, we're making that categorization, we're seeing the common characteristics, all right? So, plot K tells you distance and size. Plot J tells you composition and size. Go back to plot H, we had mass and size. And that's what we're trying to get to. We got the moons in there, all right? What it really means is we're looking for groups and common traits, okay? So, based on the data in this exercise, the organization of the solar system, how would you organize, and this is only based on the data in this exercise, okay? All right? How would you organize the solar system? Okay? Who wants to take a stab at it? You get a brave volunteer. Yes. Organize the solar system. Yes.
Why not? Size tells it all.
Size tells it all.
If I know it's a big thing, I know it's gaseous, I know where it's at in the solar system, I know how many moons or it's got.
Okay. All right. We're putting these in. How many groups would you create? All right. There are 4 groups in the solar system, right? Based upon what we've seen so far. Anyone disagree? Please. I love disagreement. All right. That you can use this data to organize the objects in the solar system into groups and categories and classification. So the homework exercise is to say, all right, so here it is. Based on the data in this exercise, the organization of the solar system can be described, I don't say it has to be described, but it can be described as 4 groups of objects with similar mass, size, composition, and distance from the sun. All right, I think we've shown that for these things, right? But you can go beyond that. We showed that with the moons, all right? If we have these 4 groups, we have the object types, which would be the composition. We have the object numbers, which you can find from that plot. And what qualities do the objects have in common? All right? This is where you're really going to extract meaning and ideas out of this. Okay? Go back through every single plot that we did. Take the 4 objects in each group. See if they have commonalities. If they don't have commonalities, make a note of that. If they do have commonalities, find out. Okay? What you might find is that the ones with ice and some rock, they tend to be more elliptical orbits. They tend to have more inclined orbits. The other groups, the rocky group, the gaseous group, they tend to have more circular orbits. Okay? You will look at each of these groups for your homework and find out all that stuff. Now, of course, you don't have to do that homework. You're the teachers. We can give you the teacher pages with our answers. But I will emphasize they are our answers and not your answers. And if you can justify it from the data, it's a correct answer. All right. Here are the teacher supplements that you're going to get. Okay? The teacher packet contains the object identification, because everybody wants to know what objects are which, right? And I'm sure some of you have already figured out a few of the objects, right? All right. Raise your hands if you have. He's definitely figured out which Jupiter is. Jupiter is the largest one, right? Okay. The one with 0 tilt has to be Earth. There you go. Okay. What's the smallest one? Some object you don't know, I guarantee, or most likely. Okay, so here are the objects, okay? We have Venus, Uranus, Ceres, which is the largest of the asteroids, Eris, which is the largest of the Kuiper Belt objects, Vesta, second largest of the asteroids, Makemake, another Kuiper Belt object, Jupiter, Pluto, Earth, Saturn, Hygeia, another asteroid, Haumea, Kuiper Belt object, Mercury, Neptune, Mars, and Pallas, another asteroid. How did I choose these objects? They are the 4 largest objects in each of the groups: the rocky planets, the giant planets, the asteroids, and the Kuiper Belt objects. All right, how many of you have heard of Kuiper Belt objects before today? How many of you have not heard of Kuiper Belt objects before today? Good, you're going to learn a lot more about them in the next hour when I give my discussion. All right. So, all right, those are the things. And next page, we've got the size versus composition with each of the objects called out. All right, so you can figure out what's your asteroids, rocky planets, Kuiper Belt object. By the way, I'll note that these documents still say gas giant planets. I have stopped saying gas giant. We haven't updated these documents yet. I just say giant planets, all right? Astronomers actually call Uranus and Neptune ice giants because their formation, they actually created more ice than they did gas. You can call Saturn a liquid giant because it's actually by volume more liquid than it is gas. Jupiter is more liquid and Saturn is more gas than liquid. So calling them gas giants is actually out of fashion these days. Okay, it's only happened in the last decade or so. I clued in about 5 years ago, and I'm now calling them just giant planets. All right, we'll update these documents when we get rid of this draft copy, not for reproduction. Okay. Here is size versus distance from the sun, again with the identifications for you. And finally, here's the making sense of the data. And so if you look at the asteroids, you can see that they've got the distances, the masses, they tend to be more elliptical, they tend to be more tilted. Notice when we use the word tend to, doesn't mean that they're always more elliptical, they aren't always more tilted, but they tend to have more of that, okay? And so these are our observations. Are they 100% accurate? Absolutely not. I do not say anything I do is 100% accurate. All right? They are our impressions, and anything you can justify with the data or your kids can justify with the data is good. Now, you have high school students. Okay, this is kind of simple for high school students. How can you jazz it up, spice it up, make it better for your high school students? All right? Oh, I'm sorry, wait a second. So basically what you come out of this is, before we go to the high school thing, is a sense of the solar system that we call a modern view of the solar system, which is the last piece thing you're getting. I'm going to ignore this for now and go to my PowerPoint version of it, which I like to call the 21st century solar system. Okay? In which, because you can organize them by distance, you have the sun at the center, which is a star, it's the only star in the solar system. You got the rocky planets around that, you have the asteroid belt around that, you have the giant planets around that, you have the Kuiper belt around that, and you have this thing called the Oort cloud that you haven't heard of yet today, but you will hear about, that's around that. And this is a simple, stupid bullseye diagram that I created when I started doing this talk 10 years ago, and it actually works really well. I thought it was kind of blasé and stupid, but you know what? It really gives you a sense of the structure of the solar system. And as we'll talk about in just a few minutes, it actually gives you a sense of the ideas of how the solar system formed. Because if you've got this hot sun in the center, where are you going to form ices? As far away as possible. So where are the icy objects? In the Kuiper belt and the Oort cloud. Rocky things, they can get heated, right? So where you can find the rocky things? Closer in. Rocky planets, asteroid belt. Okay? All right? As you'll see that is a fundamental thing. All right, so to jazz this up for your high school students, first of all, somebody said we could use an Excel spreadsheet. Yes, All right? You can do an Excel spreadsheet. You can actually have the kids make the plots themselves. They can explore the various plots, explore the various correlations, and they can go through and find the size versus mass, and the orbit tilt versus orbit inclination, and the mass versus number of moons, and so on and so forth, and see how good those other plots are that I didn't show you today, okay? But even for younger kids, you can actually use this as a vehicle for discussing what defines a planet, because in 2006, astronomers came up with the very first ever, all right? In the history of astronomy, there has never, ever been a definition of a planet, okay? And it was first defined in 2006. And that caused a lot of controversy because it kicks Pluto out of its planethood, all right? So you can read about Pluto reclassification. You can write a position paper, but I emphasize you must support the position with evidence. Give us some evidence, not I read it on Wikipedia, or Alan Stern says so, okay? No appeals to authority. If you've learned anything, justify it from some data or some evidence. And you might say, well, where am I going to learn about these Pluto reclassifications? Actually, I put together a web page for you, okay? Which has a bunch of links to planet definition, and I created a tiny URL for it. So if you go to tinyurl.com, PA-GSFC-2013-PD-LINKS, PD links, okay? That URL will take you to a web page where I have 10 or 15 different links that discuss defining a planet. From experts like Mike Brown, who discovered Eris and Haumea and Makemake, Alan Stern, who's the PI of the New Horizons mission, Hal Levinson, and even some popular folks like Neil Tyson, and I don't know if I got a Phil Plait in there or not. No, and a couple books you can look at, okay? There's a lot more on the web. I just chose some people who I knew are scientific and put relatively good arguments. And you'll notice on that web page, I also put up there that the fact that they're listed doesn't mean I agree or disagree with what they say. I know that they at least present reasonable arguments. All right?
Thank you, Frank.